Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. So in this video lecture we are going to discuss about the first shifting theorem of the Laplace transformation. So before starting with this first shifting theorem, let me revise the standard results which are related to the Laplace transformation. In our previous video lecture we already learned, so these are the 9 Laplace transformation of some standard result, and one of the important thing about these 9 results are that so these results are applicable for a single term. That means to find out the Laplace transformation of exponential function, trigonometric function, algebraic function, so these results are applicable. So now we are learning the concept which is called as the first shifting theorem. So now this first shifting theorem says that Laplace transformation of e raised to at f of t is equal to phi of s minus a, where the Laplace transformation of f of t is equal to phi of s and Laplace transformation of e raised to minus at f of t is equal to phi of s plus a. So before understanding this theorem, let me inform you that when we have to apply the first shifting theorem. So now this first shifting theorem is applicable when to find out the Laplace transformation of 2 or more than 2 term, and out of this term, first term, one of them term is exponential function. That means suppose we wish to find out the Laplace transformation of f of t is equal to e raised to 3t into sine of 2t. So now observe that this is the Laplace transformation of product of 2 term, and out of this 2 term, one term is exponential, then use the first shifting theorem. So now second example, suppose we wish to find out the Laplace transformation of e raised to 2t into t raised to suppose 5. So then again to find out the Laplace transformation of 2 term or 2 or more than 2 term, and out of which one term is exponential, then use the first shifting theorem. So this example, suppose this is e raised to 3t, then this is sine of t into cos of 3t. So this is the, so to find out the Laplace transformation of 2 or more than 2 term, and out of them one term is exponential, then use the first shifting theorem. Now let's try to understand how to apply this theorem. So now we are applying this first shifting theorem because out of this 2 term, first term is exponential function. So now first find out the Laplace transformation of this f of t. So find out the Laplace transformation of f of t. So whatever function we are getting, call that function as phi of s. Then to apply this shifting theorem, so now replace this phi of s by s minus a. That means subtract the term a from the parameter s when power of e is positive. Again, if the power of e is negative, then add the term a to the parameter s. This is called as the first shifting theorem. So in short, to use the first shifting theorem means first find out the Laplace transformation of f of t, call this as phi of s, and to apply this shifting theorem, so if power of e is positive, then subtract a from s, and if power of e is negative, then add a to the parameter s. This is called as the first shifting theorem of the Laplace transformation. Now to understand this first shifting theorem of the Laplace transformation, let me discuss some examples. Now first example, so now example is that find the Laplace transform of suppose e raised to 2t then t raised to 4. Now take the simple example. So now to find out the Laplace transformation of this function. So if we take the Laplace transformation of this function, then we get this as e raised to 2t then t raised to 4. So now friends, here observe that, so to find out the Laplace transformation of 2 term, and out of this 2 term, one term is exponential function. So in this case, So these standard results are not applicable. So because these results are applicable only for the single term, and this is the product of two term, and out of this two term, one term is exponential function. So that's why first shifting theorem is applicable. So what this first shifting theorem says that, so this theorem is of the type e raised to at f of t. So according to this theorem, first find out the value of Laplace transformation of f of t. So if we compare this theorem first part and this example part, then here the value of f of t is equal to t raised to 4. So after comparing this part and this part, we get the value of f of t as t raised to 4. So according to the standard form of this theorem, so first find out the Laplace transformation of f of t. So Laplace transformation of f of t is equal to Laplace transformation of t raised to 4. So now find out this Laplace transformation. We know that this Laplace transformation is in our standard formula. So standard formula says that Laplace transformation of t raised to n is equal to n factorial upon s raised to n plus 1. So according to this formula, we can write this as 4 factorial upon s raised to 4 plus 1. We write this as s raised to 5. So this is the value of Laplace transformation of f of t. According to this property, so denote the Laplace transformation of f of t as phi of s. So this is the value of our phi of s. Then, so to apply the shifting theorem, so therefore Laplace transformation of e raised to 2t, then t raised to 4 equal to. So according to this shifting property, so whenever plus sign is there for the power of e, so here power of e plus sign is there, then subtract the value a from the parameter s. Now if we compare this example and this example, so here we get the value of a as 2. So that means subtract 2 from parameter s. So now here numerator value is 4, which is constant, so keep constant as it is, upon this is s minus 2 raised to 5. So this is called as the first shifting theorem. So this is happened because of the first shifting theorem of the Laplace transformation. So in this way we apply the first shifting theorem for the Laplace transformation. So now to understand this, now let's take the second example as, so to find out the Laplace transformation of, now take one more simple example. So now to find out the Laplace transformation of e raised to 2t, then t raised to 3 by 2. Again simple example. So now to find out the Laplace transformation of this function e raised to 2t, then t raised to 3 by 2. Again observe that this is the product of two term, and out of this two term, one term is exponential function. So we can use the first shifting theorem. So if we compare this first shifting theorem and this example, then here the value of f of t is equal to t raised to 3 by 2. Then according to this first shifting theorem, first find out the value of Laplace transformation of f of t. We get the value of phi of s. So therefore Laplace transformation of f of t is equal to Laplace transformation of t raised to 3 by 2. So this is of the type Laplace transformation of t raised to n, so where the value of n is 3 by 2. Whenever value of n is in the form of p upon q, then gamma function of n plus 1 upon s raised to n plus 1 result is applicable. So we can write its Laplace transformation as gamma function of 3 plus 2 plus 1 upon s raised to 3 plus 2, 3 upon 2 plus 1. So if we simplify this, then we get this as gamma function of, so this is 5 by 2 upon s raised to 5 by 2. So whatever Laplace transformation of f of t we are getting, so according to this theorem, we are calling this as phi of s. So this is the value of our phi of s. Now to solve this example, therefore Laplace transformation of e raised to 2t, then t raised to 3 by 2 equal to. So according to the first shifting theorem, so here this power of e is positive, so we can write this as phi of s minus a. So here if we compare these two example, this example with this property, then the value of a is equal to 2. That means subtract 2 from the parameter s. So we can write this as gamma function of 5 by 2 as it is upon, so we can write this as s minus 2 raised to, this is 5 by 2, which is the value of your phi of s minus a. So only subtract a from the parameter s. So keep the constant term as it is. So now this is the second example. Now let's take the third example. Now next question is, suppose find the Laplace transformation of, we can take simple example, Laplace transform of e raised to minus t then cos square of 4t. So e raised to minus t cos square of, so or in simple way let's take this as 4t. So now to find out this Laplace transformation, so we write this as Laplace transformation of e raised to minus t into cos square of 4t. So again here observe that, so this Laplace transformation is the product of two term, and out of this two term, one term is exponential function. So whenever exponential function is there, use the first shifting theorem. So according to the first shifting theorem, so this is the second part, so we can compare these two, this equation with this theorem, then we get the value of f of t as, so here the value of f of t as cos square of 4t, cos square of 4t. So now according to this theorem, first find out the value of Laplace transformation of f of t and call this value as phi of s. So therefore if we take the Laplace transformation of f of t, then we get this as Laplace transformation of cos square of 4t. But so observe that this equation or this Laplace transformation is not in our standard formula. So first convert this cos square of 4t in terms of this in terms of this 9 standard result, and then we can easily find out the Laplace transformation of this function. So we know that, so here we know that cos square of t is equal to 1 plus cos of 2t upon 2. So if we apply this concept here, then we get the value of cos square of 4t is equal to 1 plus cos of 2 4s are, this is 8t upon 2. So moreover we can write this as 1 upon 2 plus 1 upon 2 into cos of 8t, or moreover we can take 1 upon 2 constant as common, and we get finally 1 plus cos of 8t. So that means we can write cos square of 4t as 1 upon 2 in bracket 1 plus cos of 8t. So that this it is possible for us to take its Laplace transformation. So therefore Laplace transformation of f of t is equal to Laplace transformation of cos square of 4t. So we can write this as 1 upon 2, this 1 upon 2 is constant, and if we apply the linear property of the Laplace transformation, then we get this as Laplace transformation of 1 plus Laplace transformation of cos of 8t. So we write this function according to the linear property of the Laplace transformation. So then we can get this as 1 upon 2. Then we know that Laplace transformation of 1, this is the standard result, Laplace transformation of 1 is 1 upon s. So according to the standard result of Laplace transformation, we can write this as 1 upon s plus, so Laplace transformation of cos of 8t. So this is of the type Laplace transformation of cos of 8t. So if we compare this with cos of 8t, then we get the value of a as 8. So then this property says that s upon s square plus a square. So we can write this as s upon s square plus a square. That means we can write this as 64. So this is the value of Laplace transformation of f of t, and according to this theorem, so mention the value of Laplace transformation of f of t as phi of s. So this is the value of phi of s. Now to find out the Laplace transformation of e raised to minus t into cos square of 4t, so we can write this term as, so after comparing this equation with this theorem, then here we get the value of a is equal to 1. E raised to minus t and e raised to at means value of a is 1. That means add 1 to the parameter s. So in this parameter s, add the term 1. So we can write this as 1 upon 2. So in bracket 1 upon s plus 1, then plus this is s plus 1 upon this is s plus 1 its square plus 64. So after simplifying denominator term, we get the final answer for this example. So now this is the fourth question for the first shifting theorem. Now let's take some more example for the practice purpose. Now let's find out the next example. Find the Laplace transformation of e raised to minus 2t, then in bracket 3 cos of 60 minus 5 sine of 60. Now take somehow critical example to understand this property of the Laplace transformation. So if we take the Laplace transformation of this function, then we get this as Laplace transformation of e raised to 2t in bracket 3 times cos of 60 minus 5 times sine of 60. So according to the linear property of the Laplace transformation, so we may write this as 3 into Laplace transformation of e raised to minus 2t. So this 3 is constant, so take outside the Laplace transformation, e raised to minus 2t into this is cos of 60 minus this is 5 or better way we can write here. So we can write this as 3, then this is Laplace transformation of e raised to minus 2t into cos of 60 minus 5 into Laplace transformation of e raised to minus 2t into sine of 6t. So now this is the step which is mentioned according to the linearity property of the Laplace transformation. Now observe that this 3 and minus 5 is constant. So now but here, so to solve this first term, so this first term is the product of two term, and out of this two term, first term is exponential function. Again for this second term, this is the product of two term, and out of this two term, one of them term is exponential function. So here we can use the first shifting theorem. So now use the first shifting theorem separately for this term and use the first shifting theorem separately for the second term. So if we compare this first term with this first shifting theorem, then here we get the value of f of t is equal to cos of 60, and again if we compare this theorem with this example, then we get the value of f of t for the second term as sine of 60. That means we get two value. For the first term we get this value, and for the second term we get this next value. So now according to this theorem, first find out the Laplace transformation and call that value as phi of s. So therefore Laplace transformation of f of t is equal to Laplace transformation of cos of 60. So now here again this is Laplace transformation of f of t, so which is equal to Laplace transformation of sine of 6t. So now if we find the Laplace transformation of this function, then this is of the type cos of at. So according to this formula, cos of at means s upon s square plus a square. So we can write this as s upon s square plus a square. Value of a is 6 here, so we can write this as 36 because 6 square is 36. Then if we find the Laplace transformation of this function, then this function or this equation is of the type Laplace transformation of sine of at, where the value of a is 6. Then this formula says that write this as a upon s square plus a square. So we can write this as 6 upon s square plus 6 are 36. So in this way we get the value of Laplace transformation of f of t. Call this as phi of s. So this is the value of phi of s for this first term, and this is the value of phi of s for the second term, because this is first term we are using separately shifting theorem, and for the second term we are using the separately shifting theorem, and this is the value of phi of s for the first term, this is the value of phi of s for the second term. Now if we apply the shifting theorem here, then we get this as 3 times. So we can get here as 3 times. Then if we here apply the shifting theorem, then here value of a is equal to 2 e raised to minus a2 2t. Then if value of a is 2, then whenever minus power is there, then add a to the parameter s. So we can write this term as, so s plus 2 upon s plus 2 its square plus 36. So this is for the first term. So we can write this for the first term. So according to the shifting theorem, so we can write this as s plus 2 upon s plus 2 its square plus 36. That means in this equation we add the term a to the parameter s. Then here middle sign is minus 5. Then according to this shifting theorem, their power of a is negative. So moreover, the value of a, after comparing this equation with this equation, we get the value of a again 2. That means add 2 to the parameter a. So here this value is 6, which is constant, upon this is s plus 2 its square plus 36. So in this way we solve the example based on the first shifting theorem. Now simplify this. So we get this as, this is 3s plus 6 upon denominator is s square plus 4s plus 4 plus 36. That means we get this as 40 minus, so this is 5 6 30 upon this is again s square plus 4s plus 4 plus 36. That means this is 40. So if we simplify this, then here denominator for the both term is same. So we can take denominator common, s square plus 4s plus 40. Then add the value of numerator, we get this as 3s plus 6 minus 30. So that means final answer to this term is 3s minus 24 upon s square plus 4s plus 40. So this is the example where we are using the shifting theorem. Now this is the critical example we solve here. Now let's take some more example again for learning the first shifting theorem. So now next example is e raised to 2t cos of t cos of 2t. So now this is the next example where we have to find out the Laplace transformation. So if we take the Laplace transformation of this function, then we get this as Laplace transformation of e raised to 2t into cos of t, then cos of 2t. So now friends, observe that, so this is the Laplace transformation of product of 3 term, and out of this 3 term, 1 term. So out of this 3 term, 1 term is exponential. That's why we are using the first shifting theorem. So according to the first shifting, so power of e is positive, so we can apply this part. So to apply this part, so if we compare this example with this part, then here we get the value of function f of t as cos of t into cos of 2t. Then this theorem says that first find out the value of Laplace transformation of f of t. Therefore, Laplace transformation of f of t is equal to Laplace transformation of cos of t into cos of 2t. So now to find out this Laplace transformation, observe that again this is the product of 2 term, so we cannot apply this standard result to find out this Laplace transformation. So now our aim is to convert this function in terms of this standard result so that we can easily find out the Laplace transformation. So here we can apply the result that 2 times cos A cos B is equal to, so we can write this as cos of A plus B plus cos of A minus B result. If we apply this result, then we get the value of this term as cos of t into cos of 2t is equal to. So after taking this 2 to the right side, we get this as 1 upon 2. Then a plus b, value of a is t plus 2t. So t plus 2t, so this value is cos of 3t, plus next value is cos of, this is t minus 2t. So we get this value as minus t. So here we get this as minus t. So but we know that cos of minus theta is equal to cos theta. So this theorem is applicable, or this term is applicable. Cos of minus theta is equal to, this is cos of theta. So according to this, we can write this as 1 upon 2, then in bracket, this is cos of 3t plus cos of t. So now we get this standard result. That means after applying standard result of trigonometric function, we get this as the first term and this is the second term, now which is in our standard form, result number 6. Now it is possible for us to apply the Laplace transformation. So therefore we can write Laplace transformation of f of t is equal to Laplace transformation of, so take the Laplace transformation of this function, so which is 1 upon 2, so in bracket cos of 3t plus this is cos of t. So now this bracket is over. So if we apply the linearity property of the Laplace transformation, then we get this as 1 upon 2 in bracket Laplace transformation of cos of 3t plus Laplace transformation of cos of t. So this is because of the linearity property of the Laplace transformation. So moreover we can write this as 1 upon 2. Then this equation is in our standard form, Laplace transformation of cos of at. Laplace transformation of cos of at is s upon s square plus a square. Here the value of a is 3. So we can write this as s upon s square plus 3 square. So we directly write this as 9 plus, so again this is of the form cos of at, but here the value of a for this second term as 1. So again apply the same result, we get this as s upon s square plus 1 square is 1. So this is the value of Laplace transformation of f of t, and according to this theorem, call this value as phi of s. So this is the value of our phi of s. Now our aim is to find out the Laplace transformation of this function. So therefore Laplace transformation of e raised to 2t into cos of t cos of 2t is equal to. So if we apply the shifting theorem, then the shifting theorem says that, so whatever phi of s we are getting here, so in this phi of s term, so subtract a from s. Here the value of a, after comparing this with term, so we get the value of a as 2. That means subtract 2 from the parameter s. So we get the answer of this term as 1 upon 2. Then this is s minus 2 upon s minus 2 its square plus 9 plus this is again s minus 2 upon s minus 2 its square plus 1. So in this way we can solve the example based on the first shifting property of the Laplace transformation. Now take some more example for the practice again. Now take some more example for the practice. Find the Laplace transformation of cos h of t into cos of t. Now this is one more example. So now take the Laplace transformation of cos h of t into cos of t. So observe that this equation is not in our standard form. So first convert this example in terms of standard form. So we may write this as e raised to t plus e raised to minus t upon 2 into cos of t. So this is the Laplace transformation of this function. Because according to the hyperbolic cos function, we write this as e raised to t plus e raised to minus t upon 2. So write down circular bracket here. So now this is the product of two terms. So if we simplify this term, then we get this as 1 upon 2, which is constant, take outside the Laplace transformation. Then remaining term is Laplace transformation of e raised to t into cos t. So we write this as e raised to t into cos t, first term. Now middle sign is plus, then Laplace transformation of e raised to minus t into cos of t. So now this is the first term and this is the second term. So now observe that, so to find out the Laplace transformation of this function and to find out the Laplace transformation of this function, so these functions are the product of two terms and out of them one term is exponential, this one term is exponential. So that's why shifting theorem is applicable. So but for this first term, so value of f of t is equal to cos t, and for this second term value of f of t is again cos of t. Find out the Laplace transformation of f of t for the first term. We get this as Laplace transformation of cos of t. Then according to this cos of at formula, which is s upon s square plus a square, so we get this as s upon s square plus 1. Again same here, Laplace transformation of f of t is equal to Laplace transformation of cos of t, which is s upon s square plus 1. So we write this term separately, this term separately. So you may write single term also, that is also possible. Then if we apply the Laplace transformation for this first term, then we get this as 1 upon 2, then in bracket. So now apply here the first shifting theorem. This is of the type e raised to at. So after comparing this example with this standard equation, then here we get the value of a as 1. That means this is positive power of e, value of a is 1. That means subtract 1 from s. Subtract a from s means a is equal to 1. Subtract 1 from s. For this phi of s, this is the value of phi of s for the first function, and this is the value of phi of s for the second function, actually which is same. So we can write this as s minus 1. So how to write this step? According to this, we can write this as s minus 1. So from this, then this is s minus 1 its square plus 1. So according to the shifting theorem, then here middle sign is plus, so we can write this as plus. Now for the second part, so for this second part, so if we compare this with the second type or second part of this shifting property, then here if power of e is negative, then value of a is equal to here minus 1, which is again same as that of 1, but here we add 1 to the parameter s. So now we write this as s plus 1 upon s plus 1 its square plus 1. So now here value of a is even though same, but here we get power plus. Whenever power is plus, then s minus a, this is the one term, and here power of e is minus, that means s plus 1, s plus a, that means we write here as s plus 1. So in this way we solve the example based on the Laplace transformation. So just simplify this term, we get the final solution of the example, so which is 1 upon 2, then s minus 1 upon s square minus 2s, then this is plus 2, again plus s plus 1 upon this is s square plus 2s plus 2. So in this way we get the example based on the Laplace transformation. So now let's take some examples for your practice. So let's solve some example as a exercise, so to test your knowledge. Now friends, to test your knowledge or to judge your capacity, so let's solve this example for the practice purpose. So only 8 examples are given here, so these are very simple. So use the first shifting theorem and solve this example easily. So friends, I hope you like this lecture. So thanks to one and all.